Welcome to this problem walkthrough. Today, we'll explore problem number 1290, titled Convert Binary Number in a Linked List to Integer. This is an engaging problem that involves linked lists and binary number operations. Stay tuned as we dive into the solution step by step. To understand the problem, imagine you are given a singly linked list. Each node in this list contains a binary digit, either 0 or 1. The order of these nodes represents a binary number, starting from the most significant bit at the head of the list to the least significant bit at the tail. Your task is to take this linked list and convert the binary number it represents into its decimal, or base 10, equivalent. For example, if the linked list nodes contain the digits 1, 0, and 1, this corresponds to the binary number 101. You will then calculate its decimal value and return it as the output. The input will always be a singly linked list, and the output will always be a single integer in decimal form. Let's break down the example where the linked list has the nodes 1, 0, and 1. The binary number formed by these nodes is 101. To convert this binary number into decimal, you calculate the value of each bit by multiplying it by 2 raised to the power of its position, starting from 0 for the least significant bit. So, in this case, you start with 1 times 2 to the power of 2, which gives 4, then add 0 times 2 to the power of 1, which is 0, and finally add 1 times 2 to the power of 0, which is 1. Adding these together, you get 4 plus 0 plus 1, which equals 5. Therefore, the output for this example is 5. Now consider another example where the linked list contains the nodes 0, 0, and 1. The binary number represented here is 001. When converting this binary number to decimal, the process remains the same. Multiply each bit by 2 raised to the power of its position. Starting with the most significant bit, we calculate 0 times 2 to the power of 2, which is 0, add 0 times 2 to the power of 1, which is also 0, and finally add 1 times 2 to the power of 0, which is 1. Adding these results gives 0 plus 0 plus 1, resulting in a decimal value of 1. Hence, the output for this example is 1. For a simpler case, imagine a linked list with just a single node containing the value 1. This linked list represents the binary number 1. Converting this binary number to decimal is straightforward. Since there's only one bit, you multiply it directly by 2 raised to the power of its position, which is 0. So, 1 times 2 to the power of 0 equals 1. Thus, the decimal equivalent of this binary number is simply 1, and the output is 1. There are a few constraints and edge cases to keep in mind. First, the linked list will always have between 1 and 30 nodes, and each node will contain either a 0 or a 1. The binary number will never have leading zeros unless the entire number is 0, which is represented by a single node with the value 0. For edge cases, if the linked list contains only one node, the binary number is equal to the value of that node, as we just saw. If all nodes have the value 0, the binary number is 0, and the output is also 0. Lastly, for the maximum case where the linked list contains 30 nodes, your solution needs to handle the conversion efficiently, as the binary number can represent a very large decimal value. To solve this problem, we evaluated 3 main approaches. The first approach, brute force with string conversion, is quite straightforward. The idea here is to traverse the linked list and concatenate each binary digit into a string. Once we have the complete binary string, we can convert it to an integer using Python's built-in int function with base 2. While the implementation is simple, it comes with some drawbacks. The string concatenation process can be inefficient, especially for long linked lists, as it requires additional space proportional to the number of nodes. This also relies heavily on Python's internal handling of large strings, which could introduce performance bottlenecks. For these reasons, this approach was deemed suboptimal. The second approach, iterative calculation using binary arithmetic, is more efficient and avoids the use of strings. The key insight here is to treat the binary number as a sequence of left-shifted bits. By starting with an initial value of 0 and iteratively updating it with each node's value, we can compute the result directly. This avoids the overhead of string operations and makes the process both faster and more space efficient. In the iterative approach, the steps are simple yet powerful. We initialize a variable, number, to 0. Then, as we traverse the linked list, we update number by multiplying it by 2 and adding the current node's value. This operation effectively shifts the bits to the left and appends the new bit at the least significant position. Once the traversal is complete, the variable number contains the final integer representation of the binary number. This approach has a time complexity of O(n), where n is the number of nodes in the linked list, since each node is visited exactly once. The space complexity is O(1), as no additional data structures are used beyond a single variable to store the result. Compared to the brute force method, this approach is significantly more efficient. We also considered a third approach, recursive calculation using binary arithmetic. This method is conceptually similar to the iterative one but uses recursion to handle the linked list traversal. At each step, the binary number is computed as twice the result of the recursive call plus the current node's value. While elegant, recursion introduces stack overhead, leading to a space complexity of O(n). This makes it less practical for large inputs, as it risks stack overflow and is generally less efficient than the iterative approach. Ultimately, we chose the iterative calculation using binary arithmetic as our final strategy. This method achieves optimal time and space efficiency, leveraging the relationship number equals number asterisk 2 plus digit to calculate the binary number directly. By avoiding the inefficiencies of string concatenation in the brute force approach and the recursion overhead in the recursive approach, this strategy strikes the perfect balance between simplicity and performance. The aha moment came from recognizing that binary arithmetic alone could handle the problem efficiently. With just a single traversal of the linked list and a constant amount of space, this approach scales well even for very large inputs. It is straightforward to implement, minimizes potential pitfalls, and is the most practical solution for converting a binary number in a linked list to its integer equivalent. In this problem, we are given a singly linked list where each node contains a binary digit, either 0 or 1. The goal is to convert the binary number represented by this linked list into its decimal integer equivalent. To solve this, we can use a brute force approach that involves string conversion. First, we initialize an empty string called binary_string. This string will serve as a container for the binary digits as we traverse the linked list. Next, we iterate through the linked list, starting from the head node and continuing until we reach the end of the list. For each node, we take its value, which will be either 0 or 1, and append it to the binary_string. This process effectively builds the binary number as a string while maintaining the correct order of digits from the linked list. Once we have the complete binary number as a string, we proceed to the conversion step. Here, we use Python's built-in int function with base 2. By calling int binary_string 2, we convert the binary string into its decimal integer form. This function interprets the string as a binary number and performs the conversion efficiently. Finally, we return the resulting integer as the output. Using a string for collecting the binary digits is convenient because it preserves the order of digits as we traverse the linked list. Additionally, leveraging Python's optimized int function eliminates the need to manually implement the binary to decimal conversion logic, saving us time and effort. Now, let's consider some important edge cases for this algorithm. First, if the linked list is empty, there are no binary digits to process, so we simply return 0. Next, if the linked list contains only one node, the result will be the value of that single node, which will either be 0 or 1. Another consideration is leading zeros in the binary number. These do not affect the final decimal value, and Python's int function handles them automatically during the conversion. In terms of data structures, we use a string, binary_string, to store the binary digits in order. Strings are an ideal choice here because they allow efficient concatenation during traversal. The input itself is a singly linked list, where each node contains one binary digit and a pointer to the next node. By traversing the list, we ensure that the digits are processed in the correct sequence. Analyzing the time and space complexity of this approach gives us a clearer understanding of its efficiency. For time complexity, traversing the linked list requires O(n) operations, where n is the number of nodes in the list. Converting the binary string to a decimal integer using the int function takes k, where k is the length of the binary string. Since the binary string's length is equivalent to the number of nodes, the total time complexity is O(n). As for space complexity, the binary underscore string requires O(n) space to store all the binary digits. The int function itself uses constant space for the conversion, so the overall space complexity remains O(n). Let's walk through an example. Consider a linked list with the binary digits 1, 0, and 1. We start with an empty binary underscore string. As we traverse, we append the value 1 from the first node, resulting in binary underscore string equals 1. Then, we append 0 from the second node, making it binary underscore string equals 10. Finally, we append 1 from the third node, giving binary underscore string equals 101. With the binary number now represented as the string 101, we move to the conversion step. Using int 101, 2, we convert this binary string into the decimal integer 5. This value is then returned as the output. Let's briefly revisit some edge cases. If the input linked list is empty, the output is 0 because there are no digits to process. For a linked list with a single node containing the value 0, the output is 0 as well. Similarly, if the single node contains the value 1, the output is 1. These edge cases ensure the algorithm handles minimal input scenarios correctly. By following this approach, we can reliably convert any binary number represented in a linked list into its decimal equivalent. This solution converts a binary number stored in a singly linked list into its decimal integer equivalent. Let's break it down step by step. 1. List node class. The list node class represents each node in the linked list. Each node contains a val, binary digit 0 or 1, and a next pointer to the next node in the list. 2. Initialization. Inside the getDecimalValue function, the result variable is initialized to 0. This variable will hold the decimal value as we process the linked list. 3. Linked list traversal. A while loop iterates through the linked list as long as the head pointer is not none, i.e., there are still nodes to process. For binary to decimal conversion, the binary number is converted to decimal using bitwise operations. Left shift. The result is left shifted by 1, result 1, which is equivalent to multiplying it by 2. This creates space for the next binary digit. Bitwise OR, the current node's value, head.val, is added to the result using the bitwise OR operation. This effectively appends the current binary digit to the result. 5. Move to next node. The head pointer is updated to the next node in the list using head equals head.next. 6. Return the result. Once the loop completes, i.e., all nodes are processed, the final result contains the decimal representation of the binary number. ###efficiency. Time complexity, O(n), where n is the number of nodes in the linked list, as we traverse each node exactly once. Space complexity, O(1), as we use only a constant amount of additional space. This approach is efficient and leverages bitwise operations for optimal performance, making it well-suited for converting binary numbers represented in a linked list to their decimal equivalents. Here, we start by defining the structure of our singly linked list using a static inner class called listNode. Each node in the linked list will have an integer value, val, and a reference to the next node, next. This class is equipped with 3 constructors, a default one that initializes just the value, and another that initializes both the value and the reference to the next node. Below this, we define our main method, getDecimalValue, which takes the head of the linked list as its parameter. Inside this method, we initialize a variable result to 0. This variable will hold the final decimal value of the binary number represented by the linked list. We then start traversing the linked list using a while loop, which continues as long as the current node, head, is not null. The key operation inside the loop is to left shift the value of result by 1, which is equivalent to multiplying it by 2, and then add the current node's value using the bitwise OR operator. This effectively appends each binary digit to the result as we iterate through the list. After processing the current node, we move to the next node in the linked list by updating head-to-head.next. This ensures that the loop continues until we've traversed all nodes. Once the loop completes, we've successfully converted the binary number in the linked list to its decimal representation, which is stored in the result variable. Finally, we return result as the output of the method. This straightforward approach efficiently combines bitwise operations and list traversal to solve the problem in a clean and concise manner. The problem involves converting a binary number, represented as a singly linked list, into its decimal equivalent. Each node in the linked list contains a binary digit, either 0 or 1. For example, consider the binary number 101, which is represented as the linked list 1-0-1. To solve this, we initialize a variable result to 0, which will hold our computed decimal value. The head pointer starts at the first node, which contains the value 1. For the first node, we use the formula result equals result1 head.val. Here, the left shift operation result1 multiplies the current result by 2, and the bitwiser operation head.val adds the current node's value. Substituting the values, we calculate result equals 0, 1, 1 equals 1. After this computation, we move the head pointer to the next node, which contains the value 0. At the second node, we repeat the computation with the formula result equals result1 head.val. The current result is 1, so we calculate result equals 1, 1, 0 equals 2. This operation shifts the binary representation of 1 to the left, effectively multiplying it by 2, and then adds the current node's value, which is 0. The updated result becomes 2. Moving to the third node, which holds the value 1, we perform the same calculation, result equals result1 head.val. Substituting the current values, we compute result equals 2, 1, 1 equals 5. The binary 10 becomes 101 after shifting and adding 1. At this point, the head pointer moves to none, indicating the end of the list. The final output is result equals 5, which is the decimal equivalent of the binary number 101. Now, let's look at a second example where the linked list represents the binary number 111. The input linked list is 1-1-1. We start by initializing result to 0, with the head pointer at the first node containing the value 1. For the first node, we calculate result equals result1 head.val. Substituting the values, result equals 0, 1, 1 equals 1. This shifts the result left by one binary place, and the OR operation incorporates the current node's value. The updated result becomes 1. The head then moves to the second node, which also contains the value 1. Applying the same formula, we compute result equals 1, 1, 1 equals 3. The left shift doubles the result to 2, and the OR operation adds the current node's value, resulting in 3. At the third node, which holds the value 1, we calculate result equals result1 head.val. Substituting the current values, result equals 3, 1, 1 equals 7. Here, the left shift doubles the result to 6, and the OR operation adds the current node's value, giving the updated result of 7. Now the head pointer moves to none, marking the end of the list. The final output is result equals 7, which is the decimal equivalent of the binary number 111. In another example, consider the binary number 0, represented by a linked list with a single node containing 0. We initialize result to 0 and point head to the node containing 0. The computation for this single node is straightforward, result equals result1 head.val, which evaluates to result equals 0, 1, 0 equals 0. The head pointer then moves to none, and the final output is result equals 0. For the single node linked list representing the binary 0, we saw that the computation results in result equals 0. This process of left shifting and applying the bitwiser operation is the key to converting binary numbers in linked lists to decimal integers efficiently. The left shift operation multiplies the current result by 2, effectively moving the binary digits one place to the left. The bitwise array incorporates the current node's value into the least significant bit of the shifted result. This algorithm is efficient because it traverses the linked list only once, resulting in a time complexity of O(n), where n is the number of nodes, and uses constant space, O(1). In summary, the algorithm processes each binary digit in sequence, shifting the accumulated result and adding the current digit at each step. This approach works for any binary number represented as a singly linked list, regardless of its length. The time complexity of the getDecimalValue function is O(n), where n represents the number of nodes in the linked list. This complexity arises because the algorithm traverses the linked list exactly once, processing each node during a single iteration. Let's break this down further. First, the traversal itself involves a while loop that iterates through all the nodes in the linked list. For a linked list with n nodes, there will be exactly n iterations. Within each iteration, two bitwise operations occur, a left shift to multiply the accumulated result by 2, and a bitwise or to add the binary value of the current node. Both of these operations are constant time, O1. Additionally, the pointer movement, where the algorithm advances to the next node in the list, is also O1 per iteration. Since all these operations are O1 and they occur n times, the total time complexity is O1 multiplied by n, resulting in O(n). The space complexity of the get decimal value function is O1, which means it uses a fixed amount of extra space regardless of the size of the linked list. Let's look at the memory usage in detail. The algorithm employs only a few variables. The result variable is a single integer used to accumulate the final decimal value. This variable takes up constant space, O1. Similarly, the head pointer, which is used to traverse the linked list, does not allocate any additional memory because it simply references existing nodes. It also requires O1 space. Importantly, the space used by the linked list itself is not considered part of the algorithm's space complexity, as the linked list is given as input. Since there is no need to store intermediate data or create new structures proportional to the size of the input, the overall space complexity remains O1. Let's compare this approach to a brute force or naive solution. A brute force method could involve first converting the linked list into a string or an array of binary digits, and then parsing the binary string into a decimal integer. This would require two passes over the linked list. The first pass, which collects the binary digits into a string or list, takes O(n) time. The second pass, which converts the binary representation into a decimal integer, also takes O(n) time. Additionally, this approach would use O(n) space to store the binary representation. In contrast, the current approach is more efficient in terms of space. It computes the decimal value directly during the traversal, eliminating the need to store intermediate results. While both approaches share the same time complexity of O(n), the current approach has the advantage of reducing space complexity to O1. This makes it a better choice when memory usage is a concern. Now, let's analyze the algorithm's performance across different scenarios. In the best case, the algorithm has a time complexity of O(n), as it needs to traverse the entire linked list regardless of the structure or content. Similarly, the average case also has a complexity of O(n), since on average, every node in the linked list must be processed. Even in the worst case, where the linked list is at its maximum size, the time complexity remains O(n), as the algorithm still processes each node exactly once. To mathematically prove the big O notation, let n represent the number of nodes in the linked list. During each iteration of the while loop, the algorithm performs a constant number of O1 operations, including the bitwise shift, or operation, and pointer movement. Since the loop iterates through all n nodes, the total time complexity is O1 multiplied by n, which equals O(n). Additionally, because no extra memory is allocated beyond a few variables, the space complexity is O1. When solving this problem, there are several common mistakes to watch out for. First, forgetting to specify the base when converting a binary string to an integer is a frequent issue. If you use int, binary_string, without specifying the base as 2, the function assumes the base is 10, leading to incorrect results. Always use int, binary_string, 2, for binary conversions. Next, overlooking the possibility of leading zeros can lead to errors, especially in edge cases. While leading zeros don't change the numerical value, ignoring them might cause flawed assumptions about the data. Another common inefficiency is using repeated string concatenation with plus equals inside a loop, which has O(n)² time complexity due to the way strings are copied. Instead, consider using a list to collect the digits and then applying join for better performance. Another pitfall to be aware of is making errors during reverse iteration. When calculating the decimal value by iterating backward and applying powers of 2, it's easy to mismanage the order of the binary digits. Remember, the binary number is usually provided in the correct order already, so reversing it unnecessarily will lead to incorrect results. Additionally, neglecting edge cases is a risky mistake. Examples include an empty linked list, a single node list, or a list containing only zeros. These edge cases can cause crashes or incorrect outputs, so it's important to handle them explicitly to ensure your solution is robust. In interviews, it's important to demonstrate a clear understanding of how binary numbers are represented and processed. You may encounter variations where the binary data is provided in different formats, such as arrays or strings, and you'll need to explain how to translate these into usable forms. Efficiency is another key factor. While brute force methods might solve the problem, they're rarely optimal. Aim for an O(n) solution, where n is the number of nodes in the linked list, and discuss the trade-offs in time and space complexity. Don't forget edge cases, such as lists with all zeros or those representing the largest binary numbers, as mentioning these explicitly shows thoroughness. Finally, discussing alternative approaches such as iterative versus recursive solutions or string-based versus direct computation can demonstrate depth in your problem-solving skills. There are multiple approaches to solving this problem, each with its own trade-offs. A straightforward method is to traverse the linked list, concatenate the binary digits into a string, and then convert the string to an integer using int, binary_string, 2. While simple to implement, this approach requires additional space for the string. A more efficient alternative is to compute the integer value directly during the traversal using result equals result *2 plus node.val. This method operates in O(n) time and O(1) space but may be slightly harder to conceptualize for beginners. Another option is the recursive approach, which calculates the integer value by traversing to the end of the list and backtracking with powers of 2. This method is elegant and demonstrates recursion skills, but it uses O(n) space for the call stack, making it less suitable for very large lists. Consider the trade-offs of each approach based on the specific constraints of the problem. Thanks for following along. We've reviewed the problem, explored the solution, and highlighted key concepts. Keep practicing similar problems to strengthen your understanding of linked lists and binary operations. See you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!